Hello, I just wanted to take a moment to talk to you about something called the pseudo-rate constant, which you're going to need in order to do some of the analysis for this lab. What is a pseudo-rate constant, right? Pseudo kind of means fake. So how are we talking about kind of a fake rate constant for a reaction? Isn't there like there's either a rate constant or there's not a rate constant? So what we're going to do is just kind of do a quick example which will help demonstrate what's going on here. So we're going to imagine a reaction, just A plus B goes to C, and it's first order both in A and B. So if we know that, we can certainly write the rate law. Rate equals K times the concentration of A times the concentration of B, both to the first power. So very simple, right? And we know that K is our rate constant. That's just kind of the definition. That's what we say it is. And so we know that the rate depends both on the concentration of A and the concentration of B. And if you wanted an experiment, you might think, oh, if you were trying to do like a reaction of crystal violet with hydroxide ion, you might think that, hey, what we're going to do is react those two things. So that's what A and B might be. So what we're going to do is we're going to do an experiment. We're going to start with known concentrations of B and known concentrations of A and look how they change over time. So we've got two different things here. Here we know that A naught, our initial concentration of A, is 0.02 molar for both ones. So you can see that they're both starting here at 0.02 molar. And what we see here is a plot showing concentration of A versus time. So this is concentration of A on our y-axis versus time. And it's showing it for two different initial concentrations of B. One is an initial concentration of B of 0.2 molar, and one is an initial concentration of B of 2 molar. And you can see, not surprisingly, when we have more B available, the reaction goes faster, and this slope right here is much steeper. And so we get two different plots for concentration versus time. So what do? It's a first order reaction. So using our integrated rate laws, we're going to plot the natural log of the concentration of A versus time. And if you remember from the form of the integrated rate law, you get that the natural log of the concentration of A at any given time is minus kT plus the natural log of the concentration of A to begin with. And so we should just find that our slope of the plot is minus k. And if k is a rate constant, our slope should be constant. It shouldn't depend on anything else. But what do we see? We see that we actually get two very different slopes. For one of them, we get negative 0.1, and the other we get negative 1.0. Those can't both be our rate constant, because our rate constant should be a constant. And it's not in this case if we're saying, hey, that's our slope. So if that's not k, what is it? And what it is it's called the pseudo-rate constant. Like, okay, so you said that twice now. What does it mean? Okay, now look at B. The concentration of B was about 0.2 molar or 2 molar. The concentration of A was 0.02 molar. So 0.2 molar B, 0.02 molar A. So what's going to happen as we react? Right, we're going to use up A, and let's say we react 100% of our A. How much B do we have left? Well, stoichiometrically, we're just going to say we have 0.2 molar B minus 0.02 molar is going to be 0.18 molar. So our B concentration didn't change by a whole lot. Right? So our B concentration is somewhat constant, not perfectly constant, but somewhat constant. It changed by 2 out of 0.02 out of 2. You know, that is about 10%. So not a huge change, not zero. But what that means is if we think about that concentration of B, it makes sense that when we had more B, the reaction went faster, and when we had less B, the reaction went slower. So what does that mean? It means that our slope actually includes the effects of that B, because B is a constant. Not perfectly constant. This isn't perfect, but it's constant enough that we can treat it as a constant, and we still get pretty good results. So when we say that our rate law here is rate equals K times the concentration of A times the concentration of B, A is the thing we're looking at. A is changing a lot over time. It might go down from 0.02 down to 0 eventually. And so it's changing a lot. So it's going to be our variable. But B here, B we said was a constant. So what we're going to do is we're going to rearrange this just by putting the B next to the K and putting a parentheses around it. So this second one looks exactly the same. It's just K times B times the concentration of A. But if we're treating B as a constant, then K times B is also a constant. And that what we're going to use there is the notation K prime. K prime is our pseudo-rate constant. It's actually not just K, but it's K times the concentration of B, if you notice how we did that substitution. So K prime equals K times the concentration of B. Okay? So if we wanted to actually solve for K, we do this. K equals K prime divided by the concentration of B. So if we look back, right, K equals K prime over B. Let's do this here. K equals K prime over the concentration of B. Let's look at it for the first plot. Our K prime, the one that we get directly from the plot, is the pseudo-rate constant. When we have more than one reactant, it's the pseudo-rate constant. And so we're going to say our K prime here is 0.10. Our units are per second. And then we're going to multiply, we're going to divide by the concentration of B. And in that first plot, the concentration of B was 0.20 molar. So 0.1 divided by 0.2 is 0.5 per molar second. So that is our actual rate constant. Let's compare that to the second one. Since that one is in orange, let's go ahead and do that one in orange. We've got that K is equal to K prime over the concentration of B. In this case, K prime was 1.0 per second, and our concentration of B was 2.0 molar, and that gives us a K of 0.5 per molar second. And you can see that these two K values, as they should be, are equal to one another. So when we've got reactions where there's multiple reactants, there's multiple things in our rate law, what we have to set up is experiments where we can get the pseudo-rate constant. So we set one concentration to be significantly lower than the other concentrations, so that as that A reacts, B is staying relatively constant. If we had C as well, we'd also keep C large, so that as A reacts, C is maintaining relatively constant. And all of those other terms that we're maintaining constant become part of the pseudo-rate constant. And the pseudo-rate constant is what we get directly off of the graph. And then we have to solve to figure out what our actual rate constant is. And that should be consistent across experiments. So it's a little complicated, but that's how it goes. I mean, you can't ignore the fact that as B changes, the reaction is going to get faster and slower because the reaction does depend on the concentration. The rate of reaction does depend on the concentration of B. So I hope that was helpful. And when you're doing your analysis, make sure that you are doing that where you're getting the pseudo-rate constant directly from the graph and calculating the actual rate constant based on any constant concentrations that you have in your system. Thanks. Have a great day.